Hello, everyone, and welcome to the Senior Design Capstone project for RoboSub. My name is Ricardo, and I am the team lead for this project. So what is RoboSub? RoboSub is an international student competition. Student teams from around the world design and build robotic submarines, otherwise known as autonomous underwater vehicles. The competition takes place every summer at the Transdeck facility in San Diego, which is a naval tasting facility dedicated for sonar and acoustics. It consists of a large pool, 300 feet by 200 feet by 38 feet deep, containing 6 million gallons of water. These are some of the sponsors for the project, all interested in the technologies that are promoted at this activity. So here are some of the examples of the tasks that the competition requires to accomplish. So there's tasks such as detecting a gate and maneuvering through it. There's a buoy with different images on each face, recognizing a certain face and maneuvering and touching that face. There are underwater paths that link each one of these tasks, pointing which direction to go. There's objects underwater made out of PVC, which we're required to pick up with some kind of articulating hand. And the last example we have here is a bin task, which requires us to drop a marker on a bin underwater. These are examples, and it's not a comprehensive list of things that we're required to accomplish. So here's a quick image of the actual facility and how things are laid out for an actual competition run. The facility itself is split up into quadrants with a practice and competition side. Each one has its own set of tasks that need to be accomplished, which have been mirrored location-wise. There's also specifically 2 tasks that require the use of acoustics and recognizing signals, which allow us to navigate to the appropriate location for which the task is located.
Hello, my name is Heriberto Gonzalez. I'll be discussing some of the technologies we came across while working on the RoboSub project. To begin, we dealt with artificial intelligence, object recognition, autonomous movement and navigation, peripheral controls, sensor data acquisition and processing. Next, I'll discuss the competition format for the 2021 RoboSub competition. Due to the COVID pandemic, the in-person competition has been replaced with an online one, where we'll be judged by 3 submissions. First being a design document, which is just a technical document explaining the work that was done on each sub. A team video, which just describes a specific sub-team of the project. And a website that timelines our progress throughout the year, along with illustrating outreach and community ties with other teams in the competition. The RoboSub project breakdown consists of 3 parts. First being the computer science senior design team, made up of 9 computer scientists who are tasked to develop the embedded software for the AUV. Second is the mechanical/electrical engineering senior design team, made up of 10 mechanical and electrical engineers tasked to design and construct an AUV. And thirdly is our RoboSub club team, made up of lower division students from all majors, tasked to build a secondary AUV for the competition. Now to break down the software team, which consists of 4 sub-teams: controls, mission planning, navigation, and computer vision. To begin, we'll start with controls.
Hello, my name is Gabriela Cortez, and this is a control subsection. Our objective was to research and develop code to create horizontal and vertical movement on the sub using PID controllers. We did not have access to the actual sub, so we created a small drone prototype to test our code and also created a graphical user interface to change the PID values. Here we have 2 images showing the thruster movement. In the top image, the red circles represent the thrusters paired to create row movement, and the blue circles represent the thrusters paired to create pitch movement. The image below shows front thrusters pairing up and the back thrusters pairing up to help balance the sub in case it were to tilt up or down. Here we have visuals of the angled thrusters pairing up to create movement. In the left image, the red circles represent the thrusters paired to help turn the sub to the right. In the right image, the blue circles represent the thrusters paired to help move the sub either to the left or to the right. Next, Sana will discuss the flowcharts for movement and of the code.
Hey everyone, my name is Sana, and I'll be going over some of the diagrams and flowcharts we made for some visual clarity. The first diagram we have here is for vertical movement control, which is responsible for moving our sub around the y-axis, also known as roll, as well as around the x-axis, which is also known as pitch. We begin by getting our input values from the IMU sensor, which gives us the current angle or location of the sub. We also get our set point values that come from the state machine node, giving us the desired position the sub needs to move to. So our PID controller algorithm takes these two input and set point values and then calculates the error value as a difference between them. It also outputs a PWM speed for our thrusters to spin at. That PWM speed then gets inputted into a mixer code, which mixes or combines the two outputs and sends the final PWM signals to our four thrusters for vertical movement. These PWM signals range anywhere from 1100 to 1900, with 1500 being neutral. In this slide, we have a very similar diagram for our horizontal movement control code, except this one controls the other four of the 8 thrusters, which are responsible for the horizontal movement of our sub. This includes the yaw movement, as well as moving the sub left or right, and forwards and backwards. Moving on to our code flowchart here, which we made to give an overview of how our code for controls would look. So we start off by importing all the necessary libraries and setting up the sensors. We then get our k-value inputs and initialize our thrusters and PIDs. Then we go to an if-else statement block to check if our IMU sensor is up and running. If it's not running or if there's anything wrong with it, then we get an error. And if it is running and everything is fine, then it goes ahead and retrieves the data that we need from the state machine node. We use this data to do some path optimization, and then we input all this information into our compute PIDs function, which generates an output that we plug into our mixer code. And then finally, it sends some signals to our thrusters, making them move or spin. Now, Albert will discuss the GUI and the prototype that we came up with.
Hello everyone, my name is Albert Chiu and I am in the control unit team. Because of the COVID-19 pandemic, we were unable to test our Arduino sketch to prove if it is working. Then we came up with some solution. The first was using Python GUI to represent motors to simulate the thruster, as you can see on the slide. The second option was to build a drone prototype to test the Arduino code, as you can see on the slide. We decided to use the second option. However, the drone prototype is very limited in what it can do. It only can be used to test a portion of the Arduino code function, only the balance code. The Arduino balance code uses the PID algorithm, which is the error correction method. PID stands for proportional, integral, and derivative. In order to get the PID algorithm working, we must come up with proportional, integral, and derivative constant value so the drone can be balanced. It is very hard to find the constant value that works. This was what we did. First, we guessed the value of the constant, and it took too much time on the testing, and it did not lead to a good result. Next, we were using a MATLAB software to simulate the drone. With MATLAB simulating, we were able to obtain good constant value for roll and pitch. With just few tests, with the constant value we obtained from the MATLAB simulating, our drone was able to reach to balance states. We are quite happy with the result. Thank you. I pass it on to my colleague, Brandon.
Hello, my name is Brandon Pham and I am part of the mission planning team. Our objective in mission planning is to implement an AI that will have control over our AUV as it goes through the course. We're also looking into how our subsystems and hardware should interact and transfer data required for the AUV to perform. Because of this, we are tasked with communicating with other subteams to establish the data that each subsystem would require from others, and also implementing the specific actions required for each task that the AUV needs to perform within the course. We also have to connect the subsystems through AI that is developed with the usage of ROS, which I will explain now. ROS is a robot operating system that consists of libraries and tools to help users with the development of various robot applications. ROS uses publishers and subscribers to transfer data between different software that is being executed. Publishers would continually broadcast the message, and then subscribers would be assigned to a publisher to listen to in order to receive their messages. This is how we would have the AUV transfer its data within the subsystems, but deciding what to do afterwards is done with the usage of Smash. Smash stands for State Machine, which is a ROS package that uses Python and is mainly used for complex applications. The AI will be consisting of state machines that will be deciding what moves are needed to complete a task. In the corner is a simple state machine flowchart to briefly explain what a state machine does. In this example, the state machine has two states that it can transition to and does so based on a specific outcome, which in this case is outcome 1, and the machine only completes its job after receiving outcome 2. Every task the AUV has to perform will be its own individual state machine, and they will all be connected as states within a larger overall state machine.
I'm Weng, and I'll be presenting the flowcharts for mission planning. So here we have a general flowchart that was created based on the 2019 RoboSub competition. So we'll start with gate, where the sub will see a gate and move towards it. Once it's moved forward past the gate, the sub will move on to pickup, where it will locate and pick up objects, such as a garlic and a crucifix. After that, it will move on to buoy state, where it will identify and touch buoys. Once it's done with that, it will move on to bins, where the sub will drop objects into bins, using a lever if needed. After bins is done, it will move on to ping state, where it will listen into pings, and it will move to the corresponding state that it recognizes. So it will move on to either torpedoes, will shoot torpedoes at targets, or it will move on to coffin, where it will have to open coffins, drop crucifixes, and then lift the coffin up to the surface. After that, it will, when one of these states is done, it will move on to the other state until all tasks are completed. Now we have state charts. These are charts that are a visual representation of the states that the robot is executing. So we'll be using gate state as an example. So here, the robot will start from state 0, and it will move on to position sub, which is a file that takes data from computer vision and uses that to determine whether or not it will move on to execute state or to utilities for resetting. Execute state is another file that contains all the substates that the sub uses to execute its task. So the arrows are what determine where the sub will move over. So success means it will execute the state, and failure here means it'll move on to utilities. All the charts are placed alongside code in GitHub. Now I'll pass it on to Kevin, who will explain navigation.
Hello everyone, my name is Kevin, and I was part of the navigation and computer vision subteams this semester. This slide is to discuss my work with navigation. The main goals this semester was to understand and resolve the current issues we had with the Blue Robotics ping sonar, which stemmed from last semester. We were to install ROS Noetic or Melodic on our machine and incorporate ROS with the Arduino connected sonar for the ability to send sensor information to other parts of the sub for object detection and to steer clear of large objects in the water. This sonar detects distances of the largest object in its direct pathway, and 3 separate ROS nodes will be sent throughout. 2 will deliver the distance of the largest object, one being in millimeters and the other in inches, because at this point in time, it is unclear which units of measurement we will be using, and the last node will send the confidence score of the measurement. Furthermore, we have encountered many issues that needed to be resolved. One issue was understanding why the Arduino Uno does not work with our device, which was resolved by using the Arduino Mega due to the firmware on the sonar sending information at 115,000 baud and the Uno only supporting 9600 baud. Another error that we needed to resolve was fixing the mismatch error with ROS and Arduino, and fixing the Arduino ROS code to receive an output that is similar to the Arduino serial monitor. In addition to the sonar device, we also set up an IMU. IMU stands for Inertial Measuring Unit and is responsible for checking the position of the sub using yaw, pitch, and roll. In other words, this is a really fancy gyroscope, and we have paired this IMU with ROS, sending out the data of the yaw, pitch, and roll within ROS nodes to controls. Next, I would like to introduce Gonzo, as he will be going over computer vision.
Hey everyone, my name is Heriberto Gonzalez. I'm the computer vision lead, and as the computer vision team, our objective include being able to detect when an object of interest is present in view of our AUV using the two cameras on board. We also need to be able to recognize and classify the various objects throughout the competition. And lastly, we need to be able to tell our submarine what we see and where in relation to the camera that object is located. Some of the tasks we accomplished this year include creating a dataset from the 2019 RoboSub competition. Due to COVID, we weren't given images to go off of this year. So we went back to an older competition to gather data for our network. And thanks to the Ohio State University RoboSub team, who provided plenty of videos from which we could extract images to train our convolutional neural network. We also accomplished the communications between the cameras and the submarine, and are able to tell our submarine what we are looking at and which way to turn in order to align with that object. Next, I'll talk a bit about how we accomplished this. The key to our computer vision system is the use of a convolutional neural network, more specifically called YOLO, which is basically a real-time object detection algorithm. Convolutional neural networks such as YOLO are deep learning algorithms which take an image as input and are able to assign importance to various aspects of an object within an image, and through time are able to learn to differentiate objects apart. We use an open source neural network framework called DarkNet, which allows us to train our convolutional neural network using our graphics card for its increased power when it comes to image processing. YOLO, which stands for You Only Look Once, has been iterated upon and for which we are using the fourth version, and is primarily used for real-time object detection. Next, Horacio will discuss a bit more about our image dataset.
My name is Horacio Mondragon, and I will be presenting image dataset. Just like we need materials such as textbooks, blogs, videos to learn new skills and test our knowledge, machine learning algorithms needs datasets to do the same thing. Since we are working with an autonomous underwater vehicle, it is essential to have images from previous competition to help us guide on what to look out for when recognizing underwater objects. As stated on the slide, videos and pictures were provided by the Ohio State University. Our goal for the competition was to focus on only 12 objects for the algorithm to recognize. Some examples of objects that needed to be identified were garlic-shaped objects, gates, crosses, and etc. The dataset consisted over a lump of 4,000 images and videos. A majority of images seem to be repeated, but we need to cover all bases of the object in question. We will have images that will cover objects in different angles, brightness, and positions. This is one of the reasons why there are so many images in the dataset when it comes to computer vision. We use software called Label IMG to label the dataset. The team and I manually inputted the labeling. The photos will be marked and fed to an algorithm, in which will generate a file called weight, and it will be the primary driver to help the sub navigate. When testing if our weight works properly to recognize the objects, it will try to draw a square around it and give us an accuracy score. The accuracy score will be in range of 0 to 100%. Of course, if the accuracy score is over 70%, it is generally a good rule that the sub recognize the object correctly. If it is under 70, we will need to provide more data to reinforce the object to get a better score.
What you are watching is the completed network model we created this year off of the 4,000 images we extracted and labeled. The network was trained over a 50-hour training cycle and had gone through 24,000 iterations and had processed over a million images. Although a lot more work needs to be done to improve the network, it is a great accomplishment and I'm extremely proud of my team for the hard work they put into creating the dataset for this model. From here on, this model will continue to improve for testing purposes for next year's team. Next, Ricardo will discuss about our team website.
As we stated before, a website is one of the aspects we are being judged on. We focused on creating a central resources for incoming students to start the onboarding process and learning all the technologies required for the project. Our previous website did not align to these new focuses, so a new website was designed. This front end was created using JavaScript and the React framework, which simplifies reusability and maintenance. Now, Heriberto is gonna take you on a quick tour of our new website.
Welcome to our website. As we continue to finalize our information for this year, the website will soon be updated with all progress made of this year. The website serves to introduce and welcome new members along with other RoboSub teams to what RoboSub is all about. Our website will include resources and workshops that the RoboSub team at Capstone does and is welcome to all RoboSub teams along with high schools and middle schools and anyone interested in robotics. Our website also includes all subs created in the past 3 years, along with the information of each sub. We will have sections for mechanical, electrical, and software sections, illustrating any work that was done in the past year. I hope you guys enjoyed exploring our new website. If you guys have any further questions or want to learn more about RoboSub and the RoboSub LA team at Cal State LA, you guys are welcome to check out our website at robosubla.com. Please keep in mind that this website is still currently being updated constantly, so keep a lookout for new information added to the site daily. Thank you.